Greetings one and all. This is another lesson on the topic of exponentials and logarithms, or just simply logs. Pure chapter 14.3 from the year 12 Pure book, done by Pearson / Edexcel. So this is the third lesson in this chapter, so hopefully you've watched the other two. As ever, we'll start with a warm-up of 4 questions. So here's the warm-up questions for you to have a go at. I will warn you, question 4 is deliberately hard. It was actually taken from a A-level paper, not AS, but a second year A-level paper as well. Regardless, have a go at them if you can, please. Pause the video now. Only play and hear my solutions once you've tried these yourself, then you get the full benefit. Okay, here are the solutions right now. So question 1, we've got a graph to sketch. A graph of y equals e to the x plus 1. And we need to label any points of intersection with the x-axis and state equations of any asymptotes. So, first of all, we need a coordinate grid, so you need an x and a y-axis. The next thing I'd suggest we do is to consider some critical points, namely where it crosses the x-axis, if at all, or the y-axis. So in terms of the y-axis intercept, what we need to do is think about the value of y when x is 0. So when x is 0, we've got that y is going to equal e to the power 0 plus 1, which is going to be 1 plus 1, which is 2. And so it's going to cross the y-axis at 2. So we need to put this in like so. The next thing we need to do is to think about what happens when x gets large. Well, when x gets large, this is going to shoot off towards infinity. A positive number to the power of something large is going to be huge. Whereas when x goes towards negative infinity, this is going to get smaller and smaller and smaller until eventually this becomes meaningless. The only thing we'll have left is this 1. What this means is, as x gets smaller and smaller, our graph will shrink down and approach the line where y is equal to 1. So this is an asymptote as well. So the asymptote at y equals 1 is where the line will approach, but will never hit. So drawing this graph, it's going to be very, very close to y equals 1 over here. And will only start getting bigger as we get more and more positive. So something like that would be the graph of y equals e to the x plus 1. Question 2. Sketch the graph of y equals e to the minus x minus 3, labelling any points of intersection of the x-axis and stating the equations of any asymptotes. Let's go one step further and see if we can find the x-axis and the y-axis intercepts. So again, we need a coordinate grid. This time, the power is a negative x. And so this is going to be a mirroring of the graph of e to the x. So rather going like this, the graph is going to be going the opposite way and shrinking down like so. As well as this, we've got this minus 3 tagged on the end. So what I'd suggest we do, first of all, is to think about what's going to happen when x is 0. So when x is 0, we're going to have that y is equal to e to the minus 0, which is just e to the 0. Anything to the power 0 is going to be 1 minus 3. That's going to give us minus 2. So it's going to cross the y-axis at minus 2, which is, let's just say that's about here. Now, what's going to happen as well when x gets large? So as x approaches infinity, y is going to approach e to the minus infinity, which is 1 over e to the nearing infinity, which is going to be 0. So it's going to approach minus 3. And so there's going to be an asymptote where y is equal to minus 3, which needs drawing on here. So that's going to be an asymptote where the curve will approach, yet never quite get to. And again, it's going to cross the y-axis at -2. So it's going to start off here very high and steep and drop down like so. So here's my hopefully not too shoddy attempt at sketching this. And going smaller, 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 without actually quite touching it. Something like this. In terms of the x-axis intercept, this question's a bit of a trick how I've written it here. So I wonder if we can find the x-axis intercept. So we're looking for when e to the minus x minus 3 is equal to 0. So we want e to the minus x equals 3. So how would we solve that? Well, we could do trial and error. I'm not actually going to tell you right now how to solve that, but in a couple of lessons' time, you will know how to solve such equations. So stick with this chapter. We'll have a way of solving these. It's got something to do with logarithms. So this is as good as we can do for this graph sketch. If you do that, I'm happy enough. Question 3, some differentiation. So first of all, we've got f of x equals 100 minus 4/5 e to the 5x. So to differentiate this, we get f dashed of x. The constant term vanishes. So the 100 just becomes 0. Whereas from last lesson, if we differentiate something where it's e to the power of a function, the constant before the x drops down to the front and multiplies this coefficient in much the same way as when we're differentiating something like x squared or 4x cubed. So the minus 4/5 is going to be multiplied by this 5 which comes to the front. Minus 4/5 times 5 becomes minus 4, and this power stays exactly as it is, so we just have minus 4 e to the 5x, and so that's part A done. Let's now have a look at part B. We now have g of x to differentiate, so let's work out g dashed of x. 100x, the 100x just becomes 100. Remember when we differentiate just single powers of x, the x vanishes and just leaves any coefficient before it. And this one, in the same way as here, the coefficient of the x in the power drops down to the front and multiplies the coefficient at the front. So the minus 4/5 is going to be multiplied by 0.5. In other words, minus 4/5 is going to be halved. So we get minus 2/5. Half of 4/5 is 2/5, if you're wondering. And then we have the same thing as before, above, e to the 0.5x. And that's the second one done. The last one, part C, y equals 100 e to the x minus 4/5 e to the minus 5x. So here, dy by dx, the first term stays precisely as it is. That does not change at all. From last lesson, where we differentiate something with a constant at the front, ke to the x, that would stay exactly the same as itself. So we get 100 e to the x. And over here we get minus 4/5 multiplied by minus 5, because this minus 5 comes to the front and multiplies this minus 4/5. However, minus 4/5 times minus 5 becomes positive 4. So we get plus 4, and this power of e stays the same, e to the minus 5x. And that's part C completed as well. Question 4. I did warn you, this is a slightly hard question, but one I reckon we can do with some effort and a bit of consistency, a bit of perseverance. So we have an open-topped fish tank. It's to be made for an aquarium. It's going to have a square horizontal base, very important, rectangular vertical sides, and a volume of 60 cubic meters. The materials cost 15 quid per square meter for the base, and £8 per square meter for the sides. So modelling the sides and base of a fish tank as laminae, that's a loan word from Latin. A lamina, plural laminae, just means an infinitely flat surface. So for example, an infinitely thin piece of paper. So that just means a surface with no thickness, essentially. In plain English, it's a surface with no thickness we need to consider or worry about. So we need to find the height of a tank that will minimise the overall cost of these materials. A question like this, I'd strongly recommend to do a sketch. So to save a bit of time, I've done one here. So we've got this tank. Now, the base is a square. So we've got a square base, very important. So let's just say, I don't know, let's call it x. So if it's x wide, x long rather, x along, it's going to be x wide. We can call the height h. Now, what we have from here, its volume is 60 cubic meters. This essentially is just a cuboid. So from this, we can deduce that x times h, in other words, x squared h, must equal 60. Because that's how you work out the volume of this. So the volume is going to be 60. That's one equation. However, if we're solving differential equations, what we could do with doing is just having one variable rather than two. So we need to minimize the cost. So we need to think about the different sizes of base and the different heights. That's just too much to think about. So what we could do is get h in terms of x. So we could say that h equals 60 divided by x squared. So let's just put this in here, because that will massively help us. So going forward, we can now think about the total surface area. So total surface area, in terms of surfaces that we need to think about. Now, it's worth just thinking about the outside surface area. We could double it up if we wanted, but it's not going to make any difference. We can just think about what we're actually working with on the outside. So for example, just the surfaces, just one surface of each side. For total surface area, well, the base is going to be x squared, and each side, because it's a square base, each side is going to have an area of x multiplied by h. It's going to be plus 4 lots of xh. But remember, we defined h in this way, so we can do one better. So instead of leaving h like this, we can swap in that h is 60 over x squared. So that equals x squared. 4 times 60 gives us 240. X divided by the x squared on the bottom here, that's going to give us 240 over x. And so this here is x squared relates to the surface area of the base. The second term is the surface area of the sides. But each surface area, base and sides, has its own cost associated with it. So the total cost well, we're told what the cost is for the base. It's 15 quid per square metre for the base. The area of the base is this, in terms of that's how many square metres the base is going to be. So the cost for the base is going to be 15 lots of the area of the base, 15x squared, plus the sides cost £8. So it's going to be the area of the sides, which is this, in square metres, multiplied by the cost per square metre. So it's going to be 8 multiplied by 240x. And that 8 comes from this fact here, that it's £8 per metre squared for the sides. So just labelling it on so you know where these numbers are coming from. This number here is the cost of the base. And this underneath is the cost of the sides. So we now need to go a bit further. we can neaten this up. So the total cost is 15x squared. 8 times 240, let's just do that. 8 times 240. That gives us 1920. X to the power minus 1. I'm going to call this total cost, let's call it C, because cost begins with a letter C. So let's just say that C equals 15x squared plus 1920x to the minus 1. We want to see how the cost is going to vary with how we change this variable x. So what we need to work out now is dc by dx. How does the cost change in relation to x? We're wanting the cost to be minimized. Remember, when we find a maximum or minimum, we're looking for the gradient function to be equal to 0. And so we need to differentiate this and then find where it's going to be minimized when this function is going to be equal to 0. So differentiating first of all, 15x squared becomes 30x. This x to the power minus 1, the minus comes to the front and multiplies the 1920. So we have minus 1920. And the power of x drops by 1 to minus 2. And like I say, that's going to be equal to 0 when C is a minimum. So let's just take this. Now it just so happens we can neaten this up a lot. We can actually divide through this whole thing by 30. What we get there is x minus 64 x to the minus 2 equals 0. We can now multiply everything through by x squared to get rid of this x to the power minus 2. That gives us x cubed minus 64 equals 0, and therefore x is going to equal the cube root of 64, which just so happens to nicely drop out as being exactly 4 cubic meters. But we didn't want to work out the base, we wanted to find the height of the tank that minimizes the overall cost. So to do this, we need to remember the height is 60 divided by x squared. So therefore, the best height, the cheapest height if you like, is going to be 60 divided by this optimal value of x we just found, which is 4 squared. So 60 divided by 4 squared, that's going to drop out and give us, let's just see, 60 divided by 4 squared, that gives us 3.75 meters. So that's the minimum, that's the best height to minimize the cost. Now, the more astute of you might be thinking, well, I found dc over dx is equal to 0, but the gradient's equal to 0 when it's a maximum or a minimum. How do I know that that's a minimum? Well, it is. You just have to trust me. Actually, no, you don't have to just trust me. This was taken from a larger question. A further part to this question was justifying that this is a minimum. What we could do here is to take the second derivative of this, d squared c over dx squared, and show that this is actually a increasing value. That d squared c over dx squared is positive. That would prove that it's going to be a minimum. But for now, if you'd like, you can just trust me that it is. Okay, so exponential functions, the main bit of this lesson. So just one quick example, then I'm going to allow you to just try some yourselves. So we've got a density of a pesticide in a given section of the field can be modelled by the below exponential equation, where P is the density of this pesticide, and T is the time in days since the pesticide was first applied. So this is mainly a message to you physicists out there. Not just physicists, maybe biologists as well, science generally. Exponentials are hugely powerful in terms of modelling. So chemistry, for example, cooling curves are exponential. Physics, exponential decay of radioactive compounds. Lots models in with exponentials. One such thing is this here. So first we need to use this model to estimate the density of pesticide after 15 days. This is dead simple, unless you panic. 15 days, t is a time in days. So all we need to do is sub in that t equals 15. So p is going to be 160 multiplied by e to the minus 0.006 times 15. So let's try that, see what our calculator spits out at us. Okay, so this gives us 160, then alpha e to the power of minus 0.006, whoops, too many nuts, multiplied by 15. And we get, roughly speaking, 146. Don't forget the units, milligrams per meter squared. So that's part A sorted. Part B, interpret the meaning of the value 160 in this model. Again, quite simple, and the marks on the mark scheme. So the marks next to the question would be a giveaway. This should be a 1-mark question, I can guarantee it. 160 is simply the initial density of pesticide. In the field. If you want convincing, I'll just show you very briefly. When t is 0 at the start of this modelling, p is going to be 160 e to the minus something 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 multiplied by 0. So it's going to be e to the minus 0, which is the same as e to the 0. Anything to the power 0 is obviously just 1. So then we have 160 multiplied by 1, which is just 160. So this is the density when t is equal to 0. Part C, show that the derivative of p with respect to t, dp over dt, is some constant multiplied by p. So all we need to do now is just to actually compute the derivative, dp over dt. And the way we do that is, remember, the power of the exponential stays exactly the same, but when we differentiate, the coefficient of the variable drops down to the front and multiplies this coefficient at the front. So we're going to have 160 multiplied by minus 0.006, and then this power and the e stays exactly the same. And so here, p is just the initial expression, which is 160, and then e to this power. And p is whatever's multiplied it. Sorry, k, rather, is whatever's multiplying this p. So we've got p here. Anything multiplying it is this thing in between, which is the minus 0.006. So first of all, I'll neaten this up. So 160 multiplied by this, let's just work this out. 160 multiplied by minus 0.006. That gives us minus 24/25, which is minus 0.96. So in a neatened up way, dp over dt is minus 0.96, e to the power minus 0.006t, and k is this value here. K was minus 0.006. Part D, we need to interpret the significance of the sign of the answer to Part C. So a little reminder, what did we get for Part C? Here it is. The sign's negative, a negative sign. So dp over dt is going to be negative for all values of t. So therefore, dp over dt is greater than 0 for all t bit of notation here. For any real number t where t is greater than 0, and if a gradient is always negative, that's just another proof that it's a decreasing function. And so p is a decreasing function. The density of a pesticide is going to decrease all the time. So in plain English, to just communicate this, we just need to write down that the density of pesticide is ever decreasing. And if something's always decreasing, and it can be modelled by an exponential, this is an example of exponential decay. Finally, part E, sketch a graph of P against T. So we worked out that when T was 0, the value of P was 160. There's no constant before this term, and so what this means is it will eventually reduce down to almost 0. It won't ever get to 0, but it will get very close to 0. In fact, what I'm going to do here, I'm just going to shift this up to give myself a bit more space to do my curve. Let's imagine 160 is there. The scale for this sketch is arbitrary, so I'm allowed to do this. I can be a bit naughty. So exponential decay is going to start off steep and go down, getting more and more shallow, as eventually it gets very, very, very close to 0, without actually quite touching 0. Looks like it's going up a tiny bit at the end, so I'll just get rid of that. There. A bit more. There we go. So that's the sketch. That will do us. The main thing is 160 is labelled, and the rest is absolutely okay. Over to you guys next. If you can turn to page 318, have a go at exercise 14, see all questions to give yourself some much needed practice on these. Again, I sound like a broken record saying this every single video. If you are stuck, please let me know. Send me an email or leave me a comment. I will endeavour to do my best to get back to you as soon as I can. Thanks for listening and tune in to the next vid. Bye for now.